Hi everyone, welcome to this video, and today we'll be talking about Kirchhoff's current law, or KCL in short, which is essentially talking about the behavior of currents when they meet nodes. So let's get a quick start on the definition of this law, and we'll be applying that later in a real-world circuit. So essentially, it really means that the algebraic sum of currents entering a node is 0. And essentially, this holds true when the algebraic sum of the currents exiting a node is calculated as well. The only thing that needs to be considered is that the calculation of the entering or exiting node currents needs to be considered consistently. So in a sense, in the bottom left structure that we have a node that several currents are entering this node. In a sense, I1 is one of them, I3 and I4. These are the three currents that are all entering this node. However, I5 and I2 are going to exit this node. In a sense, when there is no source or sink of current at this very node, whatever that comes in has to come out exactly with the same amount. In other words, if I want to write down an expression for this currents that are entering this node, I1 plus I3 plus I4, it's going to end up the same amount of the currents that are exiting that node, which in a sense is I2 plus I5. So these exiting currents, when they summed up, they are exactly the same as whatever that comes into that node. This is the main principle that we'll be applying to circuits when we meet several nodes in a complex circuitry. So let's move forward and start solving this real-world circuit. We're using the nodal analysis, or KCL, and try to find the VO in this circuit as the question is asking. So essentially, when reviewing this type of circuits, we could easily find out that we have considerable number of nodes in our circuit, that these nodes are correlated with currents entering and exiting to them. In these type of circuits that we have several branches, and mostly they are in parallel, we would be using nodal analysis, since it would be easier for us to find out what are all of the currents that are entering and exiting from this node or this node, for instance. You could also use these type of nodes at the bottom right, at the top left and top right corner as well. But then essentially these nodes wouldn't help you that much in terms of whatever current is entering and exiting, because that's exactly on the path of a current flow. So whatever we consider as the node is the interjection of several branches, such as this node or this node. So when we have these nodes recognized, we just need to find out what are the currents that are entering and exiting each one of those nodes. Let's try to label these nodes so that it would be easier for us to refer to them. So for instance, this node could be called A, and this one could be called B. So A and B are these two nodes that we have. Now, in terms of the currents, we need to first specify all of the currents that are entering or exiting each node with respect to the other part of the circuit. For instance, for node A, we have a current that is entering from the left side. There will be another current passing through this 10 ohms. There will be another current that is explicitly known as IX. So for some currents that we don't know actually what their value is, we can either label them or we can find out their value with respect to the parameters of the circuit that we already have them. So for instance, if I want to know what is the amount of the current that is passing through 20 ohms, it's available with respect to the voltage drop across that. The voltage drop across 20 ohms is with respect to this independent source of 40 volts, as well as the voltage at this node VA. So as long as we have labeled this node A, we know the voltage of this node can be called VA as well. So essentially, this current is going to be calculated with respect to the voltage drop across that, or essentially 10 volts minus VA, for instance. And in that case, this current is going to be generated from left to right. So in If I want to simplify that, 40 minus VA divided by 20 is the current that is flowing to the right side on this 20 ohm resistance. However, there is also IX that is coming down. Then what we can write for this current is that this amount of the current minus IX is going to give us the rest that is flowing to the right side. In that sense, this current going from A to B, will have a current that is equal to 40 minus VA divided by 20 minus IX. So that will be the current that is flowing in that direction. Now, we have another node here that we need to consider. What are the currents that are entering and exiting? So one of the currents is what we just calculated as this value. So that is entering node B. The other current is this dependent current source. This dependent current source depends on the value of Ix with another coefficient of 4, and that is entering to that node as well. So as long as we know for Ix, we could evaluate this value current as well. So 4Ix is also entering. There is also another current that we need to calculate on this branch. Since we know the voltage drop across this node or across this 10 ohms, we can easily find out what is the amount of the current that is passing through that. If you look closely, we can easily find out that VO is in parallel with VB. In a sense, VO is exactly the same as VB. So we can easily write down VO equals VB, and when the voltage drop across this 10 ohms is VO, it's the same as VB. So the current passing through that is simply VB divided by 10. And since the current flows from the positive terminal to the negative terminal of a voltage source, the current flow would be from top to the bottom. Or in this direction, it would be VB divided by 10. So in a sense, we now have all of the currents in all of the branches. Now we need to start writing the KCL formula. So starting at node A, we have the following KCL that we can write. The entering currents are going to be 40 minus VA divided by 20. That equals all of the currents that are exiting that node. So it would be Ix plus this current that we already found that out here. So essentially, we already have used the KCL for node A. We could have actually used a different label for node A. So let's call it that way for simplicity. Let's consider this current is going to be called IAB, for instance, which means that that is flowing from A to B. Now, if you consider the KCL in this node, the entering current is this much. The exiting currents are IX and IAB. So it would be IAB. Let me change that to capital I. Now, we also know that IAB is the same as this value, indeed. So essentially, this is IAB. So IAB, let's move on and consider node B as well. So node B, we have several entering currents, and IAB is one of them, 4IX is the other one. So we have IAB as the entering plus 4IX is the other one. That equals all of the currents that are exiting that node. In this case, it will be only VB over 10. VB over 10. So now we have apparently two equations, but in terms of the unknown parameters, we have VA, IX, IAB, and VB. So 4 parameters are unknown. So we need to consider 2 more equations to be able to solve this set of equations indeed. So we need to be able to find out the value of Ix with respect to the other parameters. For instance, we also know that the voltage at node A is called VA, as we already have used. And the voltage drop across this 20 ohms is going to be simply VA divided by VA. So the current that is Ix is simply VA divided by 20. So Ix is calculated with respect to VA. Also, there is another equation that we need to consider as IAB. So IAB is simply the subtraction of this current and this current. However, IAB can also be evaluated with respect to the voltage drop across this resistance. The voltage drop across that is simply VA minus VB. So in that sense, we have IAB equal VA minus VB divided by 10 ohms as well. That's how we can get 4 different equations that all of them are going to help us to find 4 unknown variables that we have, as you can see here. And in this case, we'll be using the method of elimination in order to move step by step to find out each unknown variable. So the first one is readily available over here. So we can use we can always use VA in terms of Ix over here. So VA is going to be 20 Ix. Let's call this as equation number 1 before getting too complicated. So this is my equation number 1. Afterwards, we need to consider we need to simplify VA with respect to Ix in different parts of this question as well. For instance, the second equation and the fourth equation are going to be similar together when you consider VA as 20 Ix. So in that case, VA is going to be with respect to Ix, and all of the other parameters are going to be exactly the same between these 2 equations. So let's do that and simplify equation, the last equation, as follows. So IAB is going to be, so I'm going to multiply both sides of the last equation by 10 so that it will be easier for us to calculate. It will be 10 IAB equals VA, which is 20 Ix minus VB. Now that I have this equation, I can couple that with this one. And in order to do that, I can multiply both sides by 10 as well. So I would say 10 IAB plus 40 Ix equals VB. We can sum up both sides of the equations. So 3 plus 2, in a sense. Equation number, if I remove the top part, so 2 and 3, if they are going to be summed up on both sides. So we have on the left side of the equation as 10AB and 10 IAB, so it would be 20 IAB. So when we have 40 Ix on the left side, have only 40 Ix. On the right side, we have VB and minus VB, so we can easily cancel them out. Then what is left on the right side is only 20 Ix equals 20 Ix. So simplifying this is going to help us find the following relationship. So 20 IAB is minus 20 Ix. So essentially IAB is the same as minus IX. Here is another equation that we need to consider in the solving of this set of equations. So IAB and IX are easily related together. And we know that VA is also can be expressed in terms of IX. Right now, we found IAB with respect to IX as well. So using this equation, or simply this equation, replacing IAB in terms of IX, we can find out VB in terms of IX as well. So essentially, I'll replace this equation here. So let's call that equation number 4. So equation number 4 is going to be used in equation number 3. And in doing so, 10 IAB, it would be minus IX plus 40 IX equals VB. But essentially it is 30 IX. So this is the next equation that we have arrived at. And let's call it equation number 5. Now, VB is known as well. We just need to find out, we just need to incorporate all of them in this equation number, in the first equation that we have arrived, our analysis. So in this one, we can write VA in terms of IX as well as IAB in terms of IX as well. So we are redefining this equation as follows. 40, I'm going to multiply both sides by 20 to have a better appearance. So 40 minus VA equals 20 times IX plus IAB. Now, instead of IAB though, we have an expression that says it is equal to minus IX. So IAB plus IX equals 0. This means that this whole part becomes 0. So it is 0, and essentially this means that VA equals 40. So that is one of the nodes voltages that we found. Now that we found VA to be 40, we can easily find IX with respect to this expression. So we can easily combine equation number, let's call this equation number 6 that we have arrived. So if we combine 6 and 1, 6 and 1, what we could get is that VA is 20 IX. However, VA is 40. So IX equals 2. So that is the final answer of the question in terms of IX. So IX is known. However, the main question is asking what is the amount of VO, or VO is essentially VB. So VB can be calculated with respect to equation number 5. Now that we have IX, we can calculate any other voltage or current in the branches. So VB is 30 times I. In a sense, VO equals VB, and that equals 30 IX, which means 30 times 2, which is 60. We've used, in a sense, two equations of 5, and this one that I would call it as 6. So 5 and 6 are going to take us to this answer. And I'm going to put it inside the final rectangle so that it will be easily recognizable. That's how we could get the answer for the output voltage in this circuit. You can see that this needs a little bit of work in terms of identifying first the currents that are passing through each element, and then applying nodal analysis on the nodes that we have identified properly. However, when we do that, we may end up with fewer number of equations compared to unknown variables. Then we have to search a little bit more in the circuit to find out other equations, such as these last two ones. They would help us to find out more relationships between unknown variables. Then it will be simple math equations that we need to solve. So here is another example that I've provided for you guys using the method of analysis that we explained in the previous slide. Try to solve the question in terms of the nodal voltages V1, V2, and V3 in this circuit as an exercise. Thank you for watching. Hit like and subscribe to the channel if you enjoyed this video.